Alright everyone, welcome to Applied Linear Algebra. My name is Professor Smith. So typically in this class we're going to be having, you'll usually be seeing me in these videos through the use of creating some notes for everyone to see. But every once in a while we're going to have these labs, and these labs are going to be really good for us to have discussion about the material. If you're in the online course, sometimes what you're going to see is that there will be assignments or things from the lab that show up on the homework. So sometimes it'll be very useful to look at the lab. Other times it'll just be some really important things that you want to learn through the lab and kind of help see connections and why we want to do these things. And today's lab is going to be a little bit of both. You'll see some of the stuff on the online homework, not so much on the scanned homework. You also have an opportunity later to do some stuff with the discussion board. Alright, so let's begin. So you can do a lot of different things with linear algebra, and specifically matrix algebra. And as we go through this lab, we're going to see a little bit of how we can do some stuff with computer graphics. So first we got to get into some definitions. An M by N matrix is a rectangular ordered arrangement, or an array, of numbers with M rows and N columns. This here is the important thing. So here we have some examples of the matrix A. We can kind of use either these square brackets that we see or these parentheses that we can use around this matrix in order to note it. We also have a matrix B, a matrix C, and a matrix D. Now, we say here that we have dimensions equal to the number of rows by the number of columns. So if we looked at, say, matrix A, so the dimension is for A, here notice that A has two rows, so remember rows are going to be these. They go left to right. That's a single row. That's a second row. So we have two rows, and we have three columns. So we would say that the dimension of A is 2 by 3. It's a 2 by 3 matrix. If we wanted the dimensions for B then, notice that B has two rows and two columns. So B is a 2 by 2 matrix. For C, C has 4 rows, but only a single column. So we would say it's a 4 by 1 matrix. And for matrix D, notice that it has only a single row, but 3 columns. So we'd say it's a 1 by 3. Alright, so now we've got a little bit of a definition to play around with for matrix and for dimensions. So let's talk about how we could go ahead and connect this to graphics. So grayscale images are stored in an ordered array or matrix. So consider this matrix A. We'll zoom in a little bit for this. So consider this matrix A, where we have these different values. Each element or entry in the matrix corresponds to a grayscale pixel. So entry in the matrix. It's corresponding to a grayscale pixel. So the grayscale values are going to vary from 0, which is just a completely black pixel, to 255, which would be a completely white pixel. The image that would be represented by this matrix A would be this image here. The upper left-hand corner has a grayscale value of 78. And so here we see that this is closer to black than it is to white. And all of these are kind of some shades in the middle here and there. So things like 3 are much darker, whereas things like 250 are almost completely white. We can use scalar multiplication to lighten or dim some sort of image. So let's consider the grayscale image for the Mona Lisa. So we've got that down here. If we wanted to go ahead and lighten her eyes, what we could do is we could select the pixels for the parts of the matrix around her eyes, and we could multiply those values by 1.4. So we go from something that's a little darker, like this, to something that is a little bit brighter to look at. So all we had to do there was just multiply all those values by 1.4. We also can invert images. So let's say we have a white pixel, and we want it to become black, and we want our black pixels to become white. In other words, we want the points 255, 0 and 0, 255 on our line. So in other words, we put in a white pixel, we spit out a black pixel, or we put in a black pixel and we spit out a white pixel. And this corresponds to the line y equals negative x plus 255. So in other words, what we do for every single value in that matrix we had before is we'd take its value, make it negative, and add 255 to it. We can also do this, though, as all the pixels at once with a matrix equation. So if we let M be our Mona Lisa matrix and B be a matrix where every entry is 255, so say for example 255, 255, I don't know how many pixels the Mona Lisa has exactly, so 255, 255. So I'm going to use these ellipses to kind of denote that the pattern is kind of staying as we go. We'll have more 255s filling up our matrix. Then what we can do is we can take our Mona Lisa matrix, flip all the values there, so change the sign of all of those entries, and add 255 to every single value. This becomes the matrix equation negative m plus b, which gives us our inverted image G, and that'll give us this image. So notice all the darker things became lighter and lighter things became darker. So let's say we wanted to take that image A we had from before, and we wanted to figure out what our resulting matrix was. So what we would do is we would take negative matrix we had, 78, 92, 59, 26, 166, 206, 26, 48, 74, 138, 165, 3, 66, 151, 250, 214, and we would add to this a matrix that was the correct size of all things, or all entries 255. So here notice that the dimensions for this A is it has 4 rows and 4 columns. So when we add a matrix to it, we need to make sure that when we add, we would go ahead and have the same dimensions. So we would put a 4 by 4 matrix of 255s. And then what we'd want to do is we want to be able to make sure we properly use this negative sign, and we'd want to add these together. For right now, I'm going to have us kind of skip this problem and come back to later. If you think you know what the answer is, I encourage you to give it a shot. But for now, we're going to kind of move on a little bit so that way we can talk about how we do these addition operations and then multiplying by a scalar. So this is multiplying by a negative 1. So the next thing that you'd want to do in the lab is you'd want to go ahead and look at something called octave. So for matrices, there is something very useful called MATLAB. But MATLAB is a proprietary programming language. What that means to us is it's very expensive, but it'd be very useful to us. So what we're going to use is the free version of MATLAB called Octave. And there's an online version at octaveonline.net. So what you want to do is you want to go to your web browser and open this up. there will be some bars to sign in. You'll want to go ahead and kind of just even use a Gmail account, I think even you can sign in with. And then you'll want to go to the command prompt. And what this will do is this will allow you to kind of type in some functions and some things and some variables, and it'll let you kind of do some nice, easy math things. And then from there, what you'll want to do is you'll want to experiment with what the command window could do. So if you type 1 plus 1 and hit enter, it'll do that. Type 10 times 7 times 11, it'll do that. If you want to go ahead and create a matrix that looks like this, you'll type the first row separated by spaces. You type the square bracket first, then the first row separated by spaces. You'll put a semicolon, and then you will go ahead and type in 0, 1, and 5. If we wanted to define the matrix B, we could go ahead and type 1 space 5 semicolon 4 space 1 and close the square bracket. We could even go so far as to save our matrix as B by saying B equals square bracket 1 space 5 semicolon 4 space 1 square bracket. Now, this is one thing you can do with Octave, which is kind of do some nice things with matrices, and as we kind of go on, you'll even see in the first homework, we can do way more with Octave than just type in some matrices and do some nice minor things. What we can also do is we can run script files that allow us to do some other cool things. So in this example, and this is something that would be a great opportunity to do for the discussion board. One thing you can do is take an image of your own and flip and do that color inversion that we had talked about to make one of your own inverted photos. Now, this is something that's very important. You'll want to go ahead, if you're using your own image, which I totally recommend, you might need to make it very small. There's a lot of ways to do this. You can open up in the Paint program. I'm sure there's plenty other ways to do it. But you want to make it small because Octave Online can only handle file sizes that are so big. So make sure you make a small enough picture. And then once you're done, you can go ahead and add it to your discussion board for this week. And that'll be kind of a great opportunity to get some easy points there. Remember, you need to make 2 discussion board posts each week. You can respond to other people if you want. You can post questions about the homework, about the notes, anything. So make sure you're active and kind of take advantage of opportunities to play around and do some fun stuff. Alright, so we talked a little bit earlier about how we'd want to do maybe some matrix operations. So say add matrices together or multiply matrices. For adding matrices, it's actually pretty easy and kind of intuitive. So the idea for adding 2 matrices together is we're going to go ahead and for each element in the matrix, we want to go ahead and add those individual values together. So for example, if we wanted to add these 2 matrices together, we would take 1 plus 0 to get 1, 2 plus 4 to get 6, 3 plus 8 to get 11, 6 plus negative 5 to get 1, negative 1 plus 1 to get 0, and 4 plus 2 to get 6. And so adding matrices is actually going to be very simple for us. Multiplying matrices are a little more difficult. So when we're looking at trying to multiply matrices, there are some things that I'm going to post on Blackboard to give you a little bit of extra help, to try to look at some stuff. There are some videos you can watch that kind of go through some more examples. And so we'll kind of go through and talk about some examples of doing these things. So let's say we wanted to go ahead and add 2 matrices together. Well, in order to add 2 matrices together, they have to have the same dimensions. This is relatively intuitive, I think. The idea is that you're trying to make sure that you add entries that are in the same position of information, and if they don't have the same position of information, it doesn't make sense to add them. So let's take a look at P and Q. P is something that has 3 rows and 4 columns. Q is something that has 6 rows and 3 columns. So here, we cannot add these. They don't have the same dimensions. If you look at B, here what we're doing is we have a matrix that has 3 rows and 4 columns, and another matrix that has 3 rows and 4 columns. So here we can add these, and we have to do that element with this. So we'll add the top left entries together, so 0 plus 1 will be 1, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 0 will also be 4, 1 plus 2 is 3, negative 1 plus 1 is 0, negative 3 plus 3 is 0, negative 1 plus negative 1 is negative 2, and then last row, negative 1 plus 2 is 1, negative 2 plus 2 is 0, 0 plus 0 is 0, and 1 plus 0 is 1. And so that's how we would do matrix additions. We just take all of those entries that are in the same position and add them together. Now, in order to do the problem that we had from before, where we were trying to adjust our matrix A right around the Mona Lisa example, we would need to do scalar multiplication. And so the idea is we can take a matrix and multiply it by a particular value. So scalar multiplication will never be undefined for matrices. So note that scalar multiplication is the thing we're talking about here. So in other words, taking an entire matrix and multiplying by a single value. So here all we're doing is we'll take every single entry and multiply it by that number. So here 3 times 1 is 3, 3 times 1 is 3, 3 times 1 is 3, 3 times 0 is 0, 3 times 2 is 6, 3 times 1 is 3, 3 times 3 is 9, negative 1 times 3 is negative 3, 2 times 3 is 6, 2 times 3 is 6, 0 times 3 is 0, and 0 times 3 is 0. And so that's how we do scalar multiplication. We take each of these entries and multiply them by this number we put in front, and that's how we get our output. Now the last thing, and this is the thing that you probably would want to watch some videos about, is matrix multiplication. So in order to multiply matrices, I'm actually going to write this down here, in order to multiply matrices, they need to have matching inner dimensions. Now what do I mean by that? So let's say we wanted to go ahead and take a 3 by 2 matrix and multiply it by a 2 by 3, or let's say a 2 by 4 matrix. If we're doing it in this order, so we'll say A is a 3 by 2 and B is a 2 by 4 matrix. So A times B. If we wanted to do this multiplication, the number of columns of A matches the number of rows of B. So they match, so we can multiply. However, if we took these same matrices, B times A, we would have a 2 by 4 matrix that we're trying to multiply by a 3 by 2 matrix. And so in this case, these don't match. So we can't multiply. So in order to kind of understand why this is, it'll be helpful for us to understand what's going on when we do matrix multiplication. So let's take a look at some of our examples up above. So here we have 3 matrices A, B, and C, or 4 matrices A, B, C, and D. Let's kind of do the dimensions of these really quick, just for some extra practice. Dimensions of A is 2 by 3. The dimensions for B is 3 by 2. The dimensions for C is again 2 by 3. And the dimensions for D is 3 rows by 1 column. Okay, now when we're doing matrix multiplication, what happens is the new matrix will have entries that are created by taking the rows of A combined with the columns of B. So you use rows of the first matrix with the columns of the second matrix. Alright, so let's go ahead and do this one. So if we wanted to create our new matrix, so if A is a 2 by 3 and B is a 3 by 2, their inner dimensions do match, and the outer dimensions determine the size of the new matrix. So this matrix we get when we multiply should have 2 rows and 2 columns. So if we want our first entry, it's in the first row and the first column. So we'll use the first row of A and the first column of B. So here what we'll do is we'll take 4 times -2 plus -4 times 3 plus 5 times -4 for the first entry. The next entry, I'm going to run out of space here, so I'm going to zoom out a little bit. The next entry will be found by taking the first row of A and combining it with the second column of B. So we'll take 4 times -2 plus -4 times -5 plus 5 times 5. Alright, so that's going to be our setup for our next entry. And now, when we want to use and figure out what the entries are in the second row of our matrix, we're going to go ahead and take the second row of A and combine it with either the first column or the second column of B, depending on where we are. So if we want to go ahead and take a look at this, we'll have 4 times -2 plus -4 times 3 plus -3 times -4. And that'll be for the row 2, column 1 entry. And then for our row 2, column 2 entry, what we'll do is we'll take 4 times -2 plus -4 times -5 plus -3 times 5. And so when we actually go ahead and do these calculations, we'll determine what those numbers are So that way we can complete our matrix multiplication. So 4 times negative 2 is negative 8. Negative 4 times 3 is negative 12. And 5 times negative 4 is negative 20. So just to keep track of all of our operations, I'm going to go ahead and use this calculator. So we have 4 times negative 2 plus negative 4 times 3 plus 5 times negative 4. And that should give us negative 40. Alright, now we can do this with the first row, second column entry. And so if we want to do that, that'll be 4 times negative 2 plus negative 4 times negative 5 plus 5 times 5. So we get 37. Now if we want to do row 2, column 1, we'll do 4 times negative 2 plus negative 4 times 3 plus negative 3 times negative 4. We get negative 8. And last but not least, for that last entry in row 2, column 2, make sure we understand this is a parenthesis over here. We have 4 times negative 2 plus negative 4 times negative 5 plus negative 3 times 5, and we get negative 3. So this matrix would be the result of our multiplication. So let's go ahead and jump down a little bit. Let's say we wanted to give out a try of taking D times A. So D, we said before, was a 3-row by 1-column matrix, and A, as we said, was a 2-row by 3-column matrix. So notice here that 1 and 2, these inner dimensions, the number of columns of D does not match the number of rows of A. So dimension mismatch occurs. So we can't multiply. So this is the thing we want to be careful of, is just checking if those dimensions are going to work for us and making sure we can multiply. Now when you go ahead and get a little more comfortable with the Octave Online stuff, what I encourage you to do is not only try to do these by hand, but also go ahead and try to type these into your computer in Octave Online just to double check your work. We've got these really useful tools. We really should make sure we try to take advantage of those to make sure we're doing the calculations correctly. But of course, you want to make sure you can still actually do this on your own, so don't use it as a crutch. Use it as kind of a double check tool, make sure you're doing things correctly. Alright, that's all for this first lab. As always, if you have questions, you can email me, or even better, talk about it on the discussion board. Get those points. Alright, see you next time.